Every single day I see comments saying, this is only 10 more FPS than that, or who cares, it's only 10 more FPS. The thing is that 10 more FPS than what? Compared to what? It's meaningless on its own. This is so frustrating, and it shows that a lot of people do not really understand what they're saying when they say one thing is 10 more FPS than another. So we're gonna talk a little bit about the connection between frames per second and what's honestly probably a better metric, which is frame time, how long a frame is on the display before switching to the next one. But whenever I bring that up, especially in the context of frame generation, I see people getting confused about the difference between frame times and latency, because these are not the same thing, although there can be a connection between them. So we're also going to talk a bit about PC latency and then how frame generation fits into that. Anyway, we got a lot to talk about, but let's start here because yes, there's going to be some math. 60 frames per second, 60 FPS. 60 FPS really means that each frame is on average on the screen for 1/60th of a second. But if you convert that to just measuring in seconds, there's a lot of kind of extra decimal points here. Seconds are really kind of too big of a measurement. Milliseconds would be more appropriate. There's 1,000 milliseconds in 1 second, so we could multiply by 1,000 to convert into milliseconds. So what this is now telling us is that if you're running a game at 60 frames per second, then what that means is each frame is on your screen for 16 2/3 seconds before it flips to the next one. At least on average, if we're talking about averages. That's a whole other issue, but anyway, let's keep going. We could have done the same calculation for any input frame rate. 50 FPS is 20 milliseconds between frames, so frame time. Your frame is on your screen for 20 milliseconds. 40 FPS would convert down to 25 milliseconds. So let's actually turn this into a function. Essentially, what you can do, because 1,000 times 1 is just 1, is you can take 1,000 and divide it by the frames per second, and you will get the frame time. You could then make this a function, really, if you wanted this to just get calculated in general. And what you'll notice is this makes a curve. So in general, what this is the x-axis here is frames per second, and the output axis, the y-axis, is frame times, how long a frame is on your screen. But again, this is curved. So what you'll see here is that when you're near 0 FPS, frames are on your screen for an extremely long time. But as your frames per second increases, there is a curve. There's a very strong curve, and it has an asymptote here. It flattens out a lot as your frames per second increase. Let's look at some specific values. If I have 10 frames per second, then that means that each frame is on my screen for 100 milliseconds on average before flipping to the next one. If I have 20 frames per second, then each frame is on my screen for 50 milliseconds. So by going just 10 more FPS, I've actually made it so my frames, each frame is flipping 50 milliseconds quicker. That is way quicker. That is extremely noticeable. Let's keep going though. Because this is curved, notice that as I go to 30 frames per second, each frame is on the screen for 33 1/3 milliseconds. So now notice that while we've, by going 10 FPS, we dropped 50 milliseconds of frame time. By going another 10 FPS, we've only dropped 16 2/3 milliseconds of frame time. Whoa, that's diminishing returns. If we go to 40 FPS, that's 25 milliseconds of frame time. Again, you can see these plotted on the curve here as they go down, right? 50 frames per second is 20 milliseconds of frame time. So now going 10 more FPS has only improved our frame times by 5 milliseconds. And now going to 60 FPS, we get to 16 2/3, etc. And you can see that if we keep going here, you'll see that the diminishing returns become ever more, diminishing. So for example, if you're going from 90 FPS to 100 FPS, you're only improving your frame times by 1.1 milliseconds. That's almost nothing. It's very hard to tell the difference between 90 FPS and 100 FPS if you have them side by side and aren't running a frame rate counter. Whereas it's very easy to tell the difference between 10 FPS and 20 FPS. It's extremely different. Now, in general, notice something. For example, using FPS as a metric is kind of counterintuitive, because that means that the difference between 30 FPS and 60 FPS in frame times, the middle is actually 40 FPS. Because going from 30 FPS to 40 FPS has the same difference as going from 40 FPS to 60 FPS, again, when measuring in frame time. So it can seem a little bit counterintuitive that way. Also, just in general, let me complain a little bit about the metric of FPS, because not only for this kind of counterintuitive way of talking about it with this curve, but also because people associate FPS with two things. Increasing the motion fluidity, which it definitely does, because you get more frames on your screen every second, so it makes the motion look more smooth. But also, it increases responsiveness, because the game can respond to user input quicker. So frames per second are measuring both of those things. But I get some people who know just enough about frame times to then get confused and think that frame times are the same thing as input latency times, and they are very much not the same thing. Let me pull up a shot from one of my YouTube videos that we could take a look at here and kind of illustrate this point. So notice that here I'm getting a little over 30 FPS on my RTX 3070 at these graphics settings, and it doesn't support frame gen, so I'm not using it here. So notice that the PC latency that it's kicking out here, that's what this number is about 54.5 milliseconds of latency. But we're over 30 frames per second. If we switch back to our chart over here, 30 frames per second should be 33.3 milliseconds of frame time. But the latency was much higher than the frame time. And that's correct, because there's a lot more that goes into PC latency or input responsiveness than just the time between frames. But also, when you introduce frame generation into the mix, things get really confusing, because that means you can increase your frame rates a lot while either not increasing or barely increasing your responsiveness. So notice that here, when I'm looking at the 4070 running frame generation times 2 and the 5070 running frame generation times 4, notice that both of them are essentially at 50 milliseconds of latency, but the frame rates are like 83, 166, etc. So this is one of the reasons why showing FPS numbers when you're talking about generated frames is so misleading. We associate, like, even if you didn't actually know these frame times at all, you associate a certain frame rate number with a certain feel. It has a certain feel. And so you know what 60 FPS feels like. You know what 100 FPS feels like. The problem is, if that 100 FPS is achieved through frame generation, it doesn't feel like that. Notice, interestingly, that 32 FPS without frame generation on the RTX 3070 isn't many milliseconds different in in latency compared to the 80 FPS or so achieved through frame generation, or even the 166 FPS achieved through multi-frame generation. All of these are just a few milliseconds off of 50 milliseconds of latency. But again, I see some people misinterpret this and think that 50 milliseconds of latency is going to feel like 20 FPS gaming. And that's wrong, because I see a lot of these comments from people who know just enough about frame times to then misinterpret what these latency numbers are telling you in my videos. I try to correct comments like that when I see them, but I can't get to all of them. 50 milliseconds of latency is not the same thing as feeling like 20 FPS. That is just very much not the case. Because again, a lot more goes into PC latency and input response than just the frame time, the time between frames. So this chart is made by NVIDIA. I found this on an NVIDIA blog, but it's one of the better charts I've seen, so I'm using it here. to describe the end-to-end system latency latency. So the end-to-end system latency starts with a user input. You click your mouse or you click a button on your keyboard. And it ends when your display actually flips a pixel in response to your input. Now, there is a lot of stuff that happens in between, and the time that it takes to do all of those things is the input responsiveness, the input latency. Now, note that when I'm using software to monitor the latency here, it is not monitoring the end-to-end latency from click to photon, from click to pixel response on your display. It's not doing that. What it's monitoring is the PC latency. The PC latency is starting once the PC receives the input from the mouse. So it doesn't have take into account the time between clicking the mouse and the PC receiving that input and having it processed. And then the PC latency ends once the frame is sent to the display, but does not take into account the time it takes the display to process that and then present the actual change in the pixels on the screen in response to that. Okay? So let's actually break this down a bit more to talk about what else is going on in between and how these frame times do factor in, but frame times are not the same thing as the system latency. Where the frame times are kind of helping things out here is, okay, so the PC receives the input response. It samples it, it runs the CPU game simulation, and then it submits a CPU frame to the GPU. Now the GPU has to finish doing whatever render it's already working on before it processes the new one that the CPU has sent to it that has that input response in it, okay? Now sometimes these can queue up. Sometimes the CPU is spitting out too many frames, the GPU can't handle it. This is what happens when you are GPU limited. The GPU so the CPU is kind of waiting on the GPU before the frame can get into the being actually processed. And then the GPU processes that, spits it out to the display. Now, by getting the CPU and the GPU spitting out frames quicker, we can now get more of these mouse inputs sampled and all of that, and it gets out to your display quicker. So that's one place that things can get sped up. Also, the render queue itself can be reduced using things like NVIDIA Reflex or AMD's Anti-Lag 2. Anti-Lag 1's a little bit different, a little bit less effective. The general idea with those technologies is they cut down on the render latency by specifically reducing the render queue. By actually kind of slightly frame rate capping things to better sync up the GPU spitting out a frame and being ready for the next one and when the CPU feeds it to the GPU. So if things aren't queuing up here, then as soon as the CPU grabs that mouse input, renders the frame and spits it out to the GPU, if there's nothing sitting in this queue, the GPU can then immediately process that and send it to the display. So that's how NVIDIA Reflex and similar technologies speed up the input responsiveness of the game. It's by reducing that render queue. Now, when you add in frame generation into the mix, things suddenly get more complicated. Because, first of all, at least when you're using NVIDIA's frame generation, it requires NVIDIA Reflex as part of it to try to help reduce the latency. So it's cutting down on the render queue, but you could have done that even when you're not using frame generation. So when I measure latency differences between not using frame generation and using frame generation, I'm using NVIDIA Reflex on both because you can. So there's no reason that would only be applied to when you're using frame generation. But using frame generation creates a bit of a queue or a buffer in a different point in this process. Now, I think I'm kind of oversimplifying this, but this is going to be effective enough to communicate the general idea. Essentially, for frame generation, before the frame is actually sent to the display, it holds it back, it buffers it a bit, so that a second frame coming in behind it is also ready. It then takes both of those frames and runs the frame generation algorithm to decide what happened in between. It's guessing what happens in between. And by guessing, I mean running a very advanced algorithm. Different frame generation algorithms use different ones and have various qualities, but that's the general idea. And when you're using multi-frame generation, it's still just taking those two rendered frames that were ready to go, it's buffering them, holding onto them, and in this case, just deciding more frames in between what happened. But essentially what's happening there is it's creating an extra buffered frame. Now, again, it uses NVIDIA Reflex to try to cut down on the render queue to make up for some of that, but it adds another queue, another buffer here before these are then sent out to the display and seen on your screen. So then when they do get sent to your screen, because it took those two you had and then inserted a bunch more, you are now getting frames showing up on your display much quicker. So your frame times go way down. There's way less time between frames. But that is not increasing the PC responsiveness because it's not getting the CPU and game rendering to process mouse inputs quicker, if that makes sense. And it's buffering a frame that would have otherwise been ready to send and put out on the display in order to hold it in time to have 2 frames from which to compute the generated frame. So that's what's going on here. Long story short, when frame rate goes up, frame time goes down. And usually that also corresponds to increased responsiveness, but not when those increase in frame rate is done through frame generation. And that's why we can see such different frame rates here, all with roughly the same latency. Again, these are all around 50 milliseconds of latency, but extremely different frame rates and frame times. The last thought I want to leave you guys with here is also, again, that because, especially now with the introduction of frame generation and all of that, there's such a difference between the things that FPS is measuring, the responsiveness and the motion fluidity, and frame generation very much helps motion fluidity, but does not help and maybe even hurts responsiveness. Frames per second is starting to be maybe not the best way to measure game performance, GPU performance, all sorts of things. It measures something, but it doesn't measure everything. And the two things that you really care about used to be tied together, the responsiveness and the motion fluidity, but they're not anymore. That's why I'm trying to find tools like this to display the latency as well as the frame times, frame time graphs, and frames per second. Because honestly, frame time graphs are better than frames per second anyway, because average frame rates don't show the frame time spikes, the stuttering, etc. So it's really a combination of these things that are required to actually describe the general experience that you're having. The frame time graph is the best way to identify stuttering and things like that. The latency is the best measure of responsiveness. And really, frames per second is just a convenient way of boiling a lot of that stuff down that is now not that great of a metric once you introduce frame generation into the mix, because it doesn't separate all of that out. So this puts GPU reviewers in a bit of a tough spot. So I'm trying my best to include some useful metrics and to do things like this that help communicate the difference between frames per second and frame times, but also the difference between latency and frame times, because again, they're not the same thing. Maybe you found this video useful and or interesting. If you did, you can always do the like and subscribe business, maybe even click the join button to directly support financially, and a huge thank you to those who have. And I hope all of you have an excellent day.